leading edge. This is CM leading edge. Okay? It's negative, but I just put it here in the positive sense. So you'll compute it will be negative. This is CM leading edge, okay? For any other x, I can transfer this actually as another lift and another force on the moment. It's the same force, but another moment, right? Cmx, correct? Which is simply Cmx is equal to the same moment at the leading edge plus Cl times x, if it's the large x, the non-dimensional one. Okay? So one particular x that we're interested in, what are the interesting x's? What the center of pressure? What's the center of pressure definition? Is the point at which what? Center of pressure. Point at which? What's the definition of the center of pressure? Point at which?
The aerodynamic forces are applying.
The aerodynamic forces are applying, which means what? Which means there is no moment, right? So the Cm is 0. So put the Cm is 0 in this equation, Cmx, to get x center of pressure. So x center of pressure is negative Cm leading edge over Cl, which is, if you divide the two equations, Cm leading edge and Cl, you will get 1 over 4 A naught plus A1 plus A over 2, A2 over 2, divided by A naught plus A1 over 2. Remember, A naught has the angle of attack in it. So whatever the right hand side comes, A naught will be alpha minus this. Okay, so A naught has the angle of attack on it. So any dependence on the angle of attack shows throughout A naught. So this immediately tells you that the center of pressure is a function of the angle of attack, right? This has alpha, this has alpha, so actually the center of pressure is a complicated function of alpha. It's the way, it's in the sense that as alpha increases, the center of pressure moves forward, so this guy increases, okay? So this is why we don't like the center of pressure to describe things. It's not fixed. If the airplane increases its angle of attack, the center of pressure will move, so we don't like it. We use a different point. You remember what's that? Anybody remembers? Aerodynamic center. Sometimes we call it the neutral point. Anybody remembers the definition of it? It's not the point at which moment is 0, please, because this is the center of pressure. Okay, I don't know why this confusion is there. What's the definition of the aerodynamic center? Anybody remembers?
The moment regard with and alpha doesn't change.
Exactly. There is no change with the angle of attack. The moment doesn't change with the angle of attack. So in our language here, I just told you that the angle of attack dependence goes through A naught, right? So from this equation, differentiate with respect to A naught and equate to 0. So the derivative of this guy with respect to A naught is negative pi over 2. This is very easy. And the derivative of this guy with respect to A naught is 2 pi. X in neutral point. You get immediately X in neutral point is quarter chord for any camber. Doesn't depend on the angle of attack, doesn't depend on anything. So this is the point at which you have lift and moment. You have lift and moment, okay? But the moment is constant. So this is the quarter chord. I have my CL, of course, it's 2 pi alpha or whatever, okay? There are other terms related to camber. And I have a moment, it's usually negative. Cm quarter chord, this is constant. And the point itself doesn't change with the angle of attack and even doesn't change with the camber. That's interesting. The thickness changes a little bit. Any question? So we got all these from the thin airfoil theory. It's very rich, you can keep going on. Actually, one of the problems that in the homework also, I have 4 problems or something, and they are all educational. We got this problem. The flap effects. So you have your airfoil, and I have a hinge here, and you deflect your flap. So you have, this is the flap angle, eta flap, and this is the flap chord ratio. lambda flat. So this should be unity 1. Okay, this is your x-axis, and this is your y. You can see now that I can do the following. I can connect this point and that point, and I look here as my camber. So this guy is my camber. I can get a function of it. It's a linear function. It's a function of line, right? Just 2 lines, and I will give you this to you. Do waste your time. So I give you the function, but go and apply the thin airfoil theory to get the effect of a flat deflection. Okay? So this is one of the problems. Another problem that they'll do with you here, and we will close up, is the curved flow. The thin airfoil theory is very rich. You can do a lot with it. Any questions so far, please? Any question? Any question? So we said we can do analysis, we can do design. The analysis, we need to solve an integral equation. If you're lucky enough and you have an easy G, you can use Sonjan inversion formula. If not, we use a series solution, and we killed it. And we got CL, CM in terms of the coefficients, center of pressure, neutral point, and you will solve the flat effect. Any question? So the curved flow, what's the curved flow? I have my airfoil. It's not subject to a single alpha, but my flow is curved in the following sense. So alpha is a function of x, locally at any point. That's okay. Can you solve this using thin airfoil theory? Well, yeah, I can do the following. I would say that this is equivalent to the following problem. This is my x. U infinity coming straight. And this, think about it. So the flow here has negative angle of attack. Okay? Then a little bit less, a little bit, here is 0, maybe here is positive. What is the angle of attack with respect to the camber? Is the angle between your flow and the tangent, right? Okay, so I'll make the tangent. I'll make the tangent such that it's the exact same equivalent angle of attack. So actually, this means that dy camber by dx, the equivalent y camber, is simply negative alpha. This is a function of x, right? So whenever you have a varying alpha, put negative sign, this is your camber, go and solve the thin airfoil theory, get the lift, pressure distribution, everything. Let's do it for a particular case. What is the particular case I have here? So this is my x, and I will rotate here. I will do pitching, but I will ignore unsteadiness. So I'm doing pitching, continuous pitching. So it's the effect of alpha dot. Okay? I'm doing pitching, so up and down or whatever, or just pitching up. When an airplane is moving and is doing a pull-up maneuver, it does pitching. Okay, so how does this pitching affect? Let's see. First of all, how does this lead to a varying angle of attack over the chord? Well, because, can you tell me, if this is x naught, large x naught or whatever, or small x naught, if this is the hinge, and this is a point at a distance x, can you tell me what's the normal velocity here? What's the normal velocity here due to this alpha dot? It's like this, right? Alpha dot times what? Alpha dot is your omega, so this is like omega r, tangential velocity. So alpha dot times what?
X minus X naught.
X minus X naught. This is very easy. And if you divide the normal speed by u infinity, then you get your alpha. Right? So this is your alpha of x. it's linearly varying. Yes, remember you have pitching, the point away from so the pitching point doesn't see anything, but this guy moves with a very large normal speed, so it has very large angle of attack, and so on and so on. Okay. So let's solve this. Let's get the effect of linear variation in the angle of attack or pitching, angular velocity effect. We know the effect of a simple geometric angle of attack alpha, it's 2 pi alpha. Okay? But what's the effect of alpha dot? What's that? Let's get it. The linear field theory will help you to get it. So how we solve it? How we solve it? Come on. How we solve this? I just said here. Right? Construct a camber that is negative alpha. So it's negative alpha dot C over U infinity large X minus X naught, large X naught, okay? And I will substitute by X as 1/2 1 plus cosine phi, the same here 1/2 1 plus cosine phi naught. So your camber is negative alpha dot C over U infinity. I have the half here, cosine phi minus cosine phi naught. This is very easy. Why? Because it's actually in terms of cosines. Here is the free term, and here is the coefficient of cosine. Here is A naught and A1 immediately, right? So remember, alpha naught minus A naught, this is the free term in your camber. So the free term here is alpha dot C over 2U infinity cosine phi naught. And negative A1 is the coefficient of cosine phi in your camber. And A2, negative A2 is the coefficient of cosine 2 phi, and so on and so. So here is negative alpha dot C over 2U infinity, right? So you got A0 and A1. My left coefficients simply, so I don't have a static angle of attack, it's all varying. So I got my A0 and A1. A0 is negative here, A1 is positive here. So my left coefficient, we just proved that it's 2 pi A0 and half A1. Let's get that. So this is 2 pi times alpha dot C over 2U infinity. I'll take it as a common factor. What's A0? So A0 is negative cosine phi naught, right? And what is A1? Here is 1, so I have half, right? I'll get this half inside, so because I need it. And half cosine phi naught, it's here. So I will add, what's that? So, okay, I will subtract a half and add a half. So this guy is now negative X naught. And we're done. My left coefficient is 2 pi times whatever coming, alpha dot C over U infinity, 3/4, this is the 3/4, minus X naught. Can you tell me what's this? Alpha dot multiplied something, and this is 3/4 minus X naught, so the distance between the 3/4 corner point and X naught. Alpha dot multiplied by this distance gives you the normal velocity at the 3/4 divided by U infinity, so this is what? This is what? This is what? Come on. Alpha dot times this distance, like I said, this distance is the distance between the 3/4 and the hinge. Alpha dot omega times this distance gives you the normal velocity at the 3/4 core point. The normal velocity multiplied by U, divided by U infinity gives you what? When the normal velocity divided by U infinity gives you what? The angle of attack. So this is the angle of attack at the 3/4 core point. This is what I told you about last time, is that by Pistorici, and Moltov. So this is an Italian aerodynamicist. Moltov is a very famous German aerodynamicist. They posed the following problem. Can we get the lift coefficient and the moment coefficient from measurement of the local angle of attack at particular points? The answer for the lift was surprising, and you can see it here from the thin airfoil theory. You just need the local angle of attack at the 3/4 point. For the leading edge, it was alpha at 0 at the leading edge, 2 alpha at half chord, minus 3 alpha at the trailing edge. And I don't remember the coefficient outside. I can look it up. And we're done, by the way, so let's go and take a break. So this is 5/16. Okay? So the first statement of theirs, you can prove it using the thin airfoil theory. It's exact, actually, it's not approximation. It's exact for a linearly varying angle of attack. If it's not linearly varying, it's a good approximation, still a good approximation. See you after.